Good evening, ladies and gentlemen. My name is Rob Norris and I'm the Dean of the Faculty of Science at Monash University. I would like to welcome you all to the 8th lecture in the Monash University 50th Anniversary Public Lecture Series. Tonight, it is my very great pleasure to introduce tonight's speaker, Professor Tim Flannery. Tim is living evidence of what can be achieved with a Monash education. He began his first higher degree and completed it, a Master of Science at Monash University in 1981. You don't look that old, Tim. An acclaimed writer, scientist and explorer, Tim was the 2007 Australian of the Year and Australian Humanist of the Year in 2005. Earlier this year, he received the Monash University Distinguished Alumni Award. Whilst arguably best known in Australia for his commentary on environmental issues, he also has a distinguished academic record in the fields of zoology and paleontology. I read an article recently that described Tim as Australia's best-known scientist. I think this is a truly deserved description, as Tim influences public opinion and drives debate about history, the environment, and climate change. He does this by communicating everywhere and through all sorts of media. This week it has almost been impossible to watch TV or read the paper without coming across comments from Tim. He is a consummate and straightforward communicator through his lectures, TV series and books. Most notably, the international bestseller, The Weather Makers, The History and Future Impact of Climate Change, is really outstanding. Ladies and gentlemen, please join me in welcoming Professor Tim Flannery.
Thanks very much for that introduction, Rob. And I don't know, I think that Monash, when I first enrolled there, wondered what they'd got, actually. I came from an arts background and they were very generous to have me at all, but anyway. Look, I reckon tonight's a great night for sustainability. Here we are, it's VFL week in Federation Square, and I reckon we've got more people to attend something to do with sustainability than we have for the footy. So, So thanks so much for coming, and thank you especially to those people who are outside the room watching this on video link. I know it's not an ideal situation, but I really very much appreciate you being here to participate in tonight's event. What I'd like to do tonight is to really take a new look at the climate problem. And you might think perhaps it'd be a broader look than certainly the current debate is all about. You might think that may not be too difficult, given that we seem fixated on whether we'll start carbon trading in 2010 or 2011. But nevertheless, I'd like to take, as I said, a broader look, one that looks beyond carbon trading to the problem as a whole, to the carbon imbalance of the planet as a whole. In order to do that, though, I really need to just briefly go back to the nature of the problem that we're dealing with, because we need to be reminded of the causes of it and how things are playing out before we can really start dealing with the solutions to that particular problem. Really, the climate problem is probably most simply phrased as being just an air pollution problem. It results from the burning of fossil fuels and the emissions of greenhouse gases into the atmosphere as a result of that process. But to understand why that is such a daunting problem for humanity, we need to know a little bit about the atmosphere itself. Now, I think one of the difficulties we've had as we've tried to come to terms with this problem is that when people look up into the sky, which we can thankfully do here, it looks as if the atmosphere just goes on forever. And people quite reasonably ask, well, how could it be that humble humanity could have any influence at all on that vast organ of our planet? It turns out that the atmosphere, or to look at the atmosphere from down here and try to estimate its size, is very, very misleading. If you want to try to gain a sense of how large the atmosphere actually is, you've got to carry out a bit of a thought experiment and imagine taking those gases that comprise the atmosphere and compressing them down about 1,000 times until they became a liquid, and then comparing them in your imagination with, say, the size of the oceans on our planet. If you were able to do that, you'd be able to see that the atmosphere is 500 times smaller than the oceans. And that really, it's the sort of most essential thing to know about our planet in this 21st century of ours, simply because small pollution sinks are much more vulnerable than larger ones. I suppose if you think about the way we deal with rubbish or things we want to throw away, emissions, you can really encapsulate it by just thinking that our planet really has three organs. We've got the rocks of the planet, the lithosphere, the oceans of our planet, and then the atmosphere. They're the three principal organs. And it's very typical of us humans. If we want to get rid of something, we just shuffle it between one organ of the planet and the other. So we've got some rubbish we don't want, we might burn it, put it into the atmosphere. We might bury it, put it into the lithosphere. Or we might flush it down the loo and put it into the ocean. And my great mate John Doyle, in that regard, has a marvellous saying. He says that the history of civilization really is just a history of connecting bums to the sea. And he's right. We couldn't have cities without it, But it's symptomatic of the way we deal with any unwanted material. And at a small scale, of course, that doesn't present any problem. That really is a genuine solution to any disposal issue we have. But on the scale that we have, on the scale that humanity exists now on the face of the planet, those sort of disposal solutions are just no longer adequate, particularly in relation to the atmosphere. It's by far the smallest of Gaia's organs. It's also extremely dynamic, so that just as an example, the breath that I'm exhaling now, some of the molecules in it in a couple of weeks' time may be over a distant continent or a distant ocean, fertilising a forest or plankton at the surface of the sea. And what that means is that the emissions that Australia puts into the atmosphere are a global problem. They're not just our problem. There are no national boundaries when you're dealing with air pollution problems, and the same for every other nation on our planet. I think the most profound thing that's ever been said about the atmosphere was said by James Lovelock, one of the great heroes of climate science, a very, very interesting man. He said that the atmosphere is a manifestation of life. He said it's every bit as much a manifestation of life as a cat's whisker is or a bird's feather is. And a feather, of course, is a manifestation of the life of an individual bird. It's not a living thing itself, but it's a manifestation of a life. The difference with the atmosphere is a manifestation of life as a whole. And as life changes, so the gaseous composition of the atmosphere must change pretty much instantaneously. And if you think about the atmosphere in those ways as being a small organ of our planet, an extremely dynamic one, and a manifestation of life, it becomes clear why air pollution has been such a persistent problem for us. And just to give you a sense of how persistent it's been, at least over my lifetime, I'm 52, I've lived through 3 separate global or near global atmospheric pollution crises. Climate change is just the third that I've seen. The first was acid rain in the 1970s, damaged vast areas across the northern hemisphere, soils and forests and so forth. The second was the ozone depletion problem, the hole in the ozone layer in the 80s. And now we face a third problem, the climate problem. I'd like, with that background, now just to have a look at this climate problem. I mentioned earlier that one of the ways that we've dealt with pollution, really the only way we've dealt with it, is simply to shuffle material between the 3 principal organs of our planet, of Gaia. Today, humans have become so very powerful that we are able to shuffle material between the 3 organs of Gaia at a very, very large level. And you can imagine, Australia is, in some senses, the world's quarry. And until you go and see some of the mines in the outback, it's hard to conceive of how very, very large scale the shuffling of materials between the organs of Gaia is. One of the things we shuffle between the organs of Gaia is carbon. We dig it up, put it into the atmosphere, into the oceans. But that's not the only element that we shuffle about. We're digging up lots of lead, for example, and we see at Mount Isa where 1 out of every 10 children now has serious levels of lead in their body. Some of the consequences of letting that material escape from the lithosphere into other parts of our planet. Mercury is another element we dig up, and incidentally, a third of the mercury that's in the food we eat comes from the burning of coal. But that is another dangerous element that we've liberated en masse from the lithosphere, put into the world's oceans and into the atmosphere in ways that are coming back to damage life on Earth. So when we think of the climate problem, it's a symptom of a more profound problem, of humans just being so successful now that we can shuffle elements between the three organs of Gaia in ways that destabilise effectively the working of life and the working of the planet. But to focus on the climate problem, how bad is it and how fast are things moving? I think as of this year we've got a far clearer view of that than we've ever had before. Up until a year or so ago, the best guide we had to those issues was the work of the Intergovernmental Panel on Climate Change, who produced a series of projections which tried to estimate how things would play out for the rest of this century in terms of the climate issue. One of the projections, and probably the most influential one that I'm sure you've all seen, concerned how much the average surface temperature of our planet may rise over the coming century. The IPCC are pretty serious and sober scientists, and the range of projections that they estimated for the century was pretty broad. At the lower end, they thought perhaps Earth might warm by as little as 1.4 degrees by the end of this century. That wouldn't be a worry to any of us. It's a small degree of warming, something that life could cope with. At the upper end of the range of projections, however, they suggested that perhaps Earth would warm by as much as 5.8 degrees. And that is such a very large warming over a short period of time, it really would almost certainly destabilise the current climate system and lay the foundations for an ice-free planet, a very different sort of planet to the one we live on today. The scientists who made those projections have remained pretty busy at the Coalface since those projections were first published in 2001. They've been measuring real-world change in terms of not only the average surface temperature of the planet, but a number of other key performance indicators of the climate system. And through the last 18 months or so, they've been publishing information about what's happening in the real world in regard to those projections. For the average surface temperature of the planet, what they've discovered is that the real world data for the early part of the curve, so from 2001 through to 2007, are right at the upper edge of the projection range. And what that means in short is that the worst case scenario is playing out before our eyes. We are on track to warm the planet by 5.8 degrees by the end of the century. Now, that's only the early part of the curve. Things may change later, but it is deeply sobering, I think, to see the real world data reflecting the worst case. For sea level, we see the same sort of thing. The projections of the IPCC for sea level rise are in fact, or the real world data I should say, in relation to the projections of the IPCC, are actually outside the envelope of the projections of the Intergovernmental Panel on Climate Change, on the high side. So sea levels are rising more rapidly than the worst case scenario. The rate of carbon dioxide accumulation in the atmosphere, which is another key indicator of how things are going, is also right at the upper end of the range. And just incidentally, tomorrow the figures for 2008, emissions for 2008, will be released. And what we'll learn, hopefully in the papers tomorrow, is that for this year, for the 12 months to the middle of the year, the amount of emissions of CO2 in the atmosphere was 2.2 parts per million. That's up from 1.8 parts per million as of the year before, as of 2007. And the rate of growth is in fact 4 times faster than at the same part of last decade. So that we're facing a runaway emissions scenario at the moment. This year, for the first time, the total volume of human emissions has exceeded 10 billion tonnes. So we're not reducing emissions. Globally, they are starting to reach runaway proportions. The full implications of that increasing burden of greenhouse gas pollution is probably seen most clearly on our planet in the high Arctic, in the Arctic ice cap. The Arctic ice cap's an ancient feature of our planet. It's been around for something like 16 million years, and it performs a key function in keeping our planet cool. After all, that 10 to 12 million square kilometres of ice that's normally present up there is very, very bright. So sunlight that falls on it during the Arctic summer is 90% of the energy in the sunlight is just reflected back into space and doesn't get to heat our planet. But as the ice melts, the dark ocean is revealed and 90% of that energy is turned into heat and serves to heat our planet. The first signs that things weren't all that good in the Arctic occurred in about 1975, and between 1975 and 2005 the Arctic ice cap started to melt away at the rate of about 8% per decade. At that rate there would still be some sort of Arctic ice cap, a very small one, but there'd be something left by about the end of this century. And although that was an alarming rate of melt, I think people took comfort in the idea that maybe it was their grandchildren's problem or their children's problem rather than their problem. In 2005, however, things changed. The rate of melt of Arctic ice increased fourfold over that summer, so it was a very dramatic increase in melt. We had a very large melt rate again in 2006. In 2007 we had the largest melt rate ever recorded, and at that point the extent of Arctic ice in summer was only 4.2 million square kilometres. This year the melt season just finished last week, and the result wasn't as bad, thank heavens, as 2007, but was very sobering. It was the second worst loss of ice ever recorded, just slightly more ice remaining at the end of summer than the year before. But this year something really odd happened in the Arctic. Scientists who've been monitoring methane in the Arctic Ocean, and they've been doing that now for 20 or 30 years, noticed something very odd. Vast bubbles of methane rising to the surface of the Arctic Ocean over very large areas, and recorded concentrations of methane in the atmosphere above the ocean about 100 times larger than background. This data has just come to light now. You'll probably read about it in the next few days in the paper. Thankfully it's occurred at the end of the melt season, so we may see some stabilisation in methane release. But there is a vast amount of methane at the bottom of the Arctic Ocean which is held in an icy substance known as clathrates. And as the water warms, the clathrates destabilise and the methane is released. Methane, of course, is a greenhouse gas that's about 20 times as potent as carbon dioxide. And the amount of methane under the Arctic ice cap is easily large enough to destabilise Earth's climate if it is released in coming years. The reason for these changes in the Arctic and in Earth's climate system, and the reason that our projections have been so conservative, was partly explained earlier in the year when a group of scientists led by Professor James Hansen of NASA went back to some of the fundamental underpinnings of the climate projections that we've used to try to work out how the climate might unfold. And what they discovered really was that if you take a slightly longer time period than the IPCC projections and try to work out the impacts of greenhouse gas over that period, the impacts of those gases on the Earth's climate system is about twice as severe as we previously imagined. With that data, they were able to have a new look at a couple of key issues for Earth's climate system, and one of those issues was the tipping point in the climate system. They were able to calibrate a bit more accurately what the tipping point of the system was, and they also identified an interesting point called the point of no return for the climate system. And basically the tipping point is that moment when there's enough greenhouse gas pollution in the atmosphere to potentially tip Earth's climate system into a new state. The point of no return is the moment when it becomes inevitable that will happen. And the reason that those 2 points in time are different is that it takes a bit of time for the heat that's trapped by the greenhouse gases to work its way through the system and cause changes such as melting ice and warming of the ocean and so forth that make further change inevitable. The view of those 9 scientists who published their data earlier in the year was that we probably passed the point of no return in terms of Earth's climate system sometime in the 1990s, latter part of the 1990s. So there was already by then enough greenhouse gas in the atmosphere to cause these changes. It's rather more difficult to determine when the point of no return will occur, but their view was that sometime before 2050, if we don't do anything, we'll be at that point of no return. They were also able to ask some very interesting questions about what we need to do in light of these new figures. They did some modelling, for example, on emissions reductions, how much we need to reduce emissions if we are to prevail over this problem. And just before I go on to that, we should just remind ourselves that in Australia our goal for emissions reductions is 60% by 2050. Yeah? And that's pretty typical of places around the world. There's a few regions and countries that are aiming for better than that, but that's about typical. And the reason we've aimed at that sort of level is that we're still basing our discussions and our policy and our economic response around the projections of the Intergovernmental Panel on Climate Change, yeah, which we now know are very conservative. And just as an example of that, the recent Garnaut reports based their understanding of the science on what's called the median projection of those of the work of the Intergovernmental Panel on Climate Change. With the new information that James Hansen and others provided for us, though, we can go back to that question of what needs to be done. What do the targets really need to be? Hansen and his colleagues said, well, would it be enough if we just stopped burning oil? Would that give us enough emissions reductions to stabilise Earth's climate system? The answer they came up with was no, it wouldn't be. What about oil and gas? So we stop burning all oil and all natural gas. Would that give us enough reductions? Again, the answer was no. You're just not getting enough heft, enough scale from that sort of activity to deal with the problem. The sort of intervention that's required, they reasoned, was something on the scale of ceasing to burn coal in conventional coal-fired power plants by around 2030. Now, if we could do that, if we could close down or retrofit with carbon capture and storage every coal-fired power plant on the planet in the next 22 years, we'd be on the road to a stabilisation that'd be adequate to deal with the problem. Very sort of overwhelming target, and I'll come back to clean coal a little bit later on, but at least that gives you a sense of the sort of large scale of interventions that are now required in order to stabilise the climate system. The good news, of course, and the stuff that I really wanted to talk to you about this evening, is that if you take a broader view of the climate problem, certain tools become evident which are sufficiently powerful to make it feasible to deal with this problem in the timescales that we have. And here could I say that the key insight is that carbon circulates through the oceans and the atmosphere and life very, very rapidly and at very large scale. If you ask the question, how much atmospheric carbon is captured by plants every year, the answer is very surprising. It's on the order of 8%. Very, very high volume. So what that tells you is that if there was no carbon going back into the atmosphere from plants dying and rotting and so forth, there would be no carbon dioxide in the atmosphere just 12 years from now. So plants provide potentially an engine for atmospheric cleansing at the scale we require to deal with the problem. The big issue for us really is how do we make solid some of those gains? How do we keep some of that carbon that plants capture out of the atmosphere? And I probably just need to say here that people misunderstand plants quite often. If you look at those trees out there, a lot of people imagine they somehow grow out of the ground. Well, they don't really. They've got their roots in the ground so they can capture moisture and gain some minerals. But they actually grow from the air. Those plants are growing by taking carbon dioxide in through their leaves, solidifying that carbon dioxide effectively to build their tissues. So a tree is little more than congealed carbon dioxide, By having a look at it, you get a rough idea of how much carbon it has sequestered out of the atmosphere. As we pursue that question of how do we make some of the gains real that plants can provide for us in terms of dealing with this air pollution problem, there are three principal tools that we can use, I believe. One of them concerns the tropical rainforests of the world. It wasn't that long ago, excuse me. It wasn't that long ago that our planet was circled by a green girdle of tropical rainforests. It's one of my great heroes is a man called Alfred Russel Wallace, and he visited the island of Singapore in 1862, and I've read his journal from that time, and he makes the throwaway remark that in 1862 an average of one Chinaman a day was being eaten by tigers on the island of Singapore. It just reminds you like how much the world has changed. There's no tigers on Singapore anymore. But the truth is that the great cities of the tropics, many of them just hardly existed 2 centuries ago. They were much, much smaller entities, villages or small towns. So over time we've cleared those tropical forests and we've released a great pulse of carbon into the atmosphere. In fact, of all of the emissions that humans put into the atmosphere, that 10 billion tonnes for this year, around 2 billion tonnes or 20% comes from the ongoing clearing of tropical forests. If we could stop that clearing and regrow tropical forests in areas where there is degraded landscapes which are of very little value to people in the tropics, we would have a very, very powerful tool for drawing carbon out of the atmosphere. Of course, people have realised that this is feasible. The Howard government, for example, committed $200 million to preserving tropical forests in Indonesia. We're yet to see much return from those sort of investments, however, and I have a particular view about why that is, and it's premised on the idea that governments in the developing world are very bad at getting any money you give them down to the village level. They're sort of like vessels, you can pour lots of money in the top and nothing comes out the bottom very much at all. And yet it's at the village level that the forests can be protected. Yes, tropical forestry is important, but there's also an enormous amount that's done at the village level in terms of tropical forest preservation, regrowth and damage and so forth. I worked for 20 years in Papua New Guinea, and in the 1980s the mountains of Papua New Guinea were truly remote places. I went back there last year, however, and was astonished to find that even in villages without electricity, people had mobile phones and they had hand cranks to provide the electricity for them. So with the right sort of mobile phone, a villager in Papua New Guinea could go online and talk directly to us. And that's exactly the sort of thing I think is going to be required if we're to sequester carbon in Earth's tropical forest at sufficient scale. We need to leap over the bad practices of government and start a direct trade, I believe, to preserve the tropical forests. I can imagine a world, perhaps just a few years from now, where people who are concerned with the security of their climate might be able to go online and visit Google Earth, for example, and have a look at villages in Papua New Guinea, and the villages may have blogs on Google Earth, and they'd say, hello, we're the X tribe, here's the land we'd love to reforest, but it's going to cost some money to do it because it's our effort involved. And if you felt inclined, you could go to an eBay-like auction site and buy some carbon in these regrowing forests. Maybe an NGO be an intermediary and hold the money in escrow for you until the forests were grown and then hand it over. But we need something at that scale. We need that direct contact at scale if we're going to unleash the full potential of the tropical rainforest to sequester carbon and stabilise our climate. What sort of gains might we get if we started reforesting degraded grasslands and degraded forests in the tropics? Hard to get figures on that, very little work's been done. But generally people would consider that if we can't be sequestering 5 gigatons of carbon, 5 billion tonnes of carbon,